When most of us picture a volcano, we probably think of, well, that classic cone-shaped mountain, right? Dramatically spewing lava.
The iconic image.
But the reality is just so much more complex
Yeah.
and really fascinating. Even the word volcano, it takes us back to ancient beliefs.
Yeah, from the Roman god Vulcan and the island volcano.
It's a great reminder that for centuries, these geological powerhouses were kind of seen as, myth and legend.
And what's fascinating is how that view shifted. Instead of fiery gods, we now see volcanoes as, well, tangible evidence of Earth's restless interior.
Constantly at work, reshaping the surface.
Exactly.
And to really get a sense of that raw power, Pompeii, you just have to think about Pompeii.
Oh, absolutely. Vesuvius, 79 CE. Such a vivid, tragic snapshot.
Yeah, imagine a bustling Roman town.
Yeah.
First the tremors, then this colossal cloud billowing into the sky. It wasn't immediately lava, was it?
No, not at first. It was more like the sky itself was falling. Ash, pumice stones raining down.
Plunging the city into darkness.
Right. And the sheer weight of it collapsing roofs. Horrific. But the really devastating part, the killer blow, was the pyroclastic flow.
Okay, describe that.
Yeah.
Because it sounds terrifying.
Picture a superheated avalanche. Ash, pumice, gas, moving like a fluid incredibly fast down the volcano's side.
And it just buried Pompeii.
Instantly, the speed, the heat, almost impossible to really comprehend. It's like a landscape eraser. Wipes out everything in seconds. That's the power we're talking about.
Wow. And in a really eerie twist, that destruction, it also preserved things, didn't it?
It did. The ash acted like a time capsule, entombing Pompeii and Herculaneum.
So archaeologists found this incredibly detailed glimpse into Roman life.
Exactly. And those plaster casts of the victims.
Oh, yeah.
So poignant. Such a human connection to that overwhelming force.
It really hits home how sudden and unpredictable these events can be. Life changes in an instant.
Mm-hmm.
So that's our way in. In this deep dive, we're going beyond just the dramatic images. We want to explore the whole story of volcanoes.
Right. What they produce, how they erupt in different ways.
The dangers they pose, which are very real, and their influence on the planet overall.
Yeah, it's a huge topic.
Okay, let's unpack this. Starting with the basics.
Yeah.
What actually comes out of a volcano?
Fundamentally, you get three main kinds of material. You've got lava flows, molten rock, then pyroclastic debris that's fragmented stuff, and various gases.
And how these behave depends on the magma underneath, right?
Right.
The molten rock itself.
Absolutely. It all comes down to the properties of that magma.
Okay, so lava. How it behaves, whether it's like a river of fire or just a thick blob, that's about viscosity, isn't it? It's resistance to flow.
Exactly. And the key player controlling viscosity is silica content, SiO2.
Silica. How does that work?
Well, think of silica molecules wanting to link up, forming chains in the melt.
Okay.
The more silica, the more chains, the more tangled they get. Makes the lava thicker, stickier, more viscous.
So low silica means runny lava.
Right, like basaltic lava, the kind you see in Hawaii. Low silica, low viscosity, it flows easily.
And high silica.
That's rhyolitic lava, jam-packed with silica, incredibly viscous, very sticky, doesn't like to flow.
So silica is like the traffic controller for lava flow.
That's a good way to put it. Yeah, it dictates how easily it moves.
Okay, let's dive into these flows then. Basaltic lava, low viscosity, super hot. It can move fast, right?
It really can. On steep slopes, it can reach up to, say, 30 kilometers an hour.
Wow.
And it can travel huge distances, sometimes hundreds of kilometers.
How does it stay molten for so long?
Ah, that's interesting. As the surface cools, it forms a solid crust.
Like insulation.
Exactly, an insulating blanket. It keeps the lava underneath molten, allowing it to keep flowing, sometimes even through underground channels. Lava tubes?
Lava tubes. Like a plumbing system for molten rock.
Precisely.
And you get those different surface textures too. Boho?
Oh.
That's the smooth, ropey-looking one.
That's the one. Forms when the surface is still hot and pasty, kind of wrinkles as the flow underneath moves.
And the other one?
Aya ore. That's when the surface cools, hardens, then breaks up into this jagged, really rough, clinkery surface because the flow continues.
Sounds like something you wouldn't want to walk on.
Definitely not barefoot.
And then there's that cool pattern when basalt cools. Columnar jointing, like Devil's Postpile.
Yes. Those amazing polygonal columns. It happens because the lava contracts as it cools and solidifies.
So it fractures in this really regular way.
Mm-hmm. The Giant's Causeway in Northern Ireland is another fantastic example, just breathtaking.
And if it erupts underwater?
Then you get pillow lava. The rapid cooling causes it to form these rounded, bulbous, pillow-like shapes.
You can see examples of that.
Oh, yeah. There's great exposed pillow lava in Cyprus, for instance. Shows how much volcanic activity shapes the ocean floor.
Okay, now what about the stickier stuff, the andesitic and rhyolitic lavas? They don't exactly race downhill, do they?
Not at all. Andesitic lava, higher silica, higher viscosity. It forms shorter, thicker flows, moves really slowly, maybe just a few meters a day.
And the surface?
As it moves, the solidified surface breaks into angular chunks. We call that blocky lava.
Blocky lava. Makes sense. And rhyolite, the stickiest.
That's the molasses of the lava world. So viscous, it often just piles up right over the vent.
Forming lava domes.
Exactly, like at Panam Crater in California.
Yeah.
Sometimes it even solidifies in the vent and gets pushed up like a spine. Rhyolitic flows themselves are rare, and always short and blocky.
Okay, so that's the liquid rock. But volcanoes throw out solid stuff too, right? Pyroclastic debris. Sounds dramatic.
It can be very dramatic. Pyroclastic debris is basically any fragmented igneous material ejected forcefully during an eruption.
Like what happened with Paricutín, the volcano that grew in a cornfield.
That's a perfect example. The rapid pileup of cinders there really showed the power of these eruptions. Cinders are just one type pea to golf ball sized glassy fragments, often full of holes. That's called scoria.
So what other kinds of pyroclastic bits do we get, especially from those runnier basaltic eruptions?
Well, gas bubbles bursting at the surface create lava fountains. Those droplets cool in the air.
Forming cinders.
Right. But you also get these amazing hair-like strands of volcanic glass. Pele's hair.
Named after the Hawaiian goddess.
Yep. And Pele's tears, small, streamlined, glassy beads. Then there are bigger pieces, blocks, which are angular chunks of older, solid volcanic rock ripped off.
Okay.
And bombs. Bombs are ejected molten or semi-molten, so they get streamlined as they fly through the air and solidify.
Hawaii must be a great place to see all that.
It really is. Classic examples there.
Now, shifting to the more explosive eruptions and andesitic, rhyolitic, the debris gets finer then, right? Volcanic ash?
Absolutely. Higher viscosity, more trapped gas equals much more violent explosions.
So ash is tiny glass particles.
Very fine, glassy particles, yeah. Less than 2 millimeters. Formed when frothy lava or pumice shatters explosively or when existing rock gets pulverized.
And you also mentioned pumice lapilli.
Angular fragments of pumice and accretionary lapilli. Those are interesting, kind of like little ash snowballs.
How do they form?
Ash particles clump together, often around a water droplet within the turbulent eruption column.
And all this loose stuff, ash, luele, it can become solid rock eventually. Tough.
Exactly. When layers of this pyroclastic material get buried and compacted, they lithify into tuff.
Sometimes it welds together.
Yeah, if the fragments are still really hot when they land, they can fuse. That's welded tuff. More commonly, though, minerals precipitate from groundwater circulating through the deposit and cement the grains together.
Where can you see good examples of tuff?
Oh, places like Hole in the Wall in the Mojave Desert or parts of New Mexico have some really striking tuff formations.
Okay, so we have molten rock, solid fragments.
Yeah.
What's the third product? Gases.
Gases, yeah. Magma contains dissolved volatiles, mostly water vapor, H2O, carbon dioxide, CO2, sulfur dioxide, SO2, and hydrogen sulfide, H2S.
And the stickier felsic lavas hold more gas.
Interestingly, yes, up to about 9% by weight sometimes.
How do the gases get out?
As magma rises, the pressure decreases, so the gases come out of solution, like opening a soda bottle fizz. Crystallization of minerals can also force dissolved gases out of the remaining melt.
And some of these gases are pretty smelly and maybe hazardous. That sulfur smell.
Definitely. Sulfur dioxide and hydrogen sulfide give you that rotten egg smell. And SO2 can react with water in the atmosphere to form tiny droplets of sulfuric acid, corrosive aerosols.
Nasty stuff. How does viscosity affect how the gas escapes?
Big difference. In low viscosity mafic magma, like basalt, bubbles can rise and escape relatively easily.
Leading to steam vents.
Right. And the bubbles that get trapped as the lava cools create vesicles, those little holes you see in rocks, like scoria.
Makes sense. What about high viscosity felsic magma?
Gases have a much harder time escaping. The magma becomes a froth as it rises.
Right.
When that froth cools and solidifies quickly, you get pumice.
So full of bubbles, it's lightweight.
Exactly. Can even float on water sometimes. You can see steam vents in places like Alaska, and vesicles are super common in basalt, like around Sunset Crater in Arizona.
So volcanoes aren't just building land, they're constantly interacting with the atmosphere. Okay, we've got the materials down. Now, how are these systems actually structured? What's underneath a volcano?
Well, deep down, there's usually a magma chamber, a reservoir where molten rock collects in the crust.
Okay.
From there, magma travels upwards through a conduit, could be a pipe-like structure or a linear crack, a fissure.
And it reaches the surface at a vent.
Right. Eruptions can happen at the main summit vent or sometimes through fractures on the volcano's sides. Those are flank eruptions.
And at the top, you often see a crater, that bowl shape. How does that form?
Couple of ways. It might just be the buildup of erupted material around the vent, or it can form if the ground collapses into the conduit after an eruption drains it.
And then you get the really big ones, calderas. They look massive.
They are. Calderas form after huge eruptions empty a significant part of the magma chamber below. The overlying volcanic structure then collapses inwards into that void.
So it's a collapse feature.
Exactly. Often many kilometers across, hundreds of meters deep. Steep inner walls, flat floor. Sometimes they fill with water, like Crater Lake in Oregon. That's a classic caldera.
Just imagine the scale of the eruption needed to create that.
Immense. Think of a balloon deflating, causing the top to sag inward. That's kind of the idea.
Now, the shapes of volcanoes vary so much. Broad shields, steep cinder cones, those classic stratovolcanoes. What controls the shape?
It's mainly down to the lava viscosity and the type of eruption products.
So shield volcanoes, like in Hawaii.
Yeah.
They're from runny lava.
Exactly. Built up by layers and layers of fluid, low-viscosity basaltic lava flows that spread out really far, creates those broad, gentle slopes.
When cinder cones, they look much steeper.
They are, formed by the pileup of ejected basaltic lapilli and blocks the coarser pyroclastic stuff during smaller explosive eruptions. Makes a steep cone shape.
And stratovolcanoes, like Mount Fuji or Mount St. Helens. They look more complex.
They are complex, also called composite volcanoes, built over long times by alternating layers strata of more viscous lava flows and pyroclastic debris.
Usually andesitic or desitic lavas.
Often, yeah. More viscous, leading to potentially more explosive eruptions, too. And their classic tone shape isn't static landslides, debris flows, big explosions can all modify them over time.
And volcanoes come in all sizes, right?
Oh, absolutely. From little cinder cones to enormous shield volcanoes and those massive supervolcano calderas. Huge range.
Okay, structures make sense.
Yeah.
Now, how do they actually erupt? We've mentioned effusive versus explosive. What's the key difference?
It really boils down to magma viscosity and gas content again. Effusive eruptions are relatively gentle. You get lava pouring out or fountaining.
Like Hawaii's lava flows or lava lake.
Exactly. Low viscosity basaltic lava. The drivers are magma buoyancy, pressure from overlying rock, and gas bubbles forming and expanding. If the conduit narrows, it can increase pressure and cause those lava fountains.
So more of a steady release. Explosive eruptions sound.
Well, much more violent. They are. Forceful ejection of pyroclastic debris, and there's a whole spectrum of intensity.
Okay, let's break down some of the smaller explosive types. Strombolian.
Named after Stromboli in Italy. Frequent, relatively small bursts ejecting clots of glowing lava that become scoria-lapilli and ash. Often makes those nice glowing arcs.
At Vulcanian.
Bigger, more explosive eruption of more viscous magma, throws out lots of scoria-lapilli and forms tall, cauliflower-shaped ash plumes.
What about when water gets involved? Phreatic and phreomagmatic.
Good question. Phreatic eruptions are steam explosions. Groundwater hits hot rock or magma, flashes to steam instantly, boom. Ejects steam, ash, bits of the surrounding rock, but usually very little new magma.
Just steam power.
Pretty much. Phreatomagmatic is a mix. Magma interacts explosively with groundwater or seawater. Lots of steam plus eruption of wet ash, lapillar lava blocks.
Like Surtsian.
Exactly. That's a type of phreatomagmatic eruption where magma hits shallow seawater, creates really violent steam explosions, like when the island of Surtsey formed off Iceland.
Okay. And then the really big ones. Plinian eruptions. They sound incredibly dangerous.
Plinian eruptions are immense, yes. Involve andesitic or rhyolitic magma, very rich in dissolved gases.
So the gas is trapped in sticky magma.
Right. The bubbles expand, coalesce. Eventually, the pressure is too much, and the magma fragments explosively.
Releasing huge amounts of energy.
Enormous pressure. It blasts vast volumes of pyroclastic material high into the atmosphere. Can even destroy the top of the volcano. Vesuvius in 79 CE, Pinatubo in 91, classic Plinian events.
And that huge eruption column we see in pictures, that's typical.
Definitely. It has distinct parts. A lower gas thrust region, a rising convective plume driven by heat, and way up in the stratosphere, an ash umbrella spreads out.
And pyroclastic flows often come from these.
Very often. If the column gets too dense, it collapses and sends those ground-hugging avalanches of hot ash, pumice, and gas racing downslope. Extremely hazardous.
And the rocks formed are different. Airfall tuff versus ignimbrite.
Correct. Airfall tuff is from ash settling out of the tall column. Ignimbrite is the deposit left by a pyroclastic flow, often welded because it was so hot.
And finally, supervolcanoes. Are they actually real?
Oh, they're very real. Eruptions on a scale that just dwarfs anything in recorded history. Hundreds, even thousands of cubic kilometers of pyroclastic debris forms enormous calderas.
Like Yellowstone.
Yellowstone is the prime example of past supervolcanic eruptions. The scale is almost mind-boggling.
Truly hard to imagine. Now, volcanoes aren't just random, are they? They pop up in specific geological settings.
That's right. Volcanism is strongly linked to plate tectonics. Most are along plate boundaries, but you also get them at hot spots and in continental rifts.
Let's start underwater. Mid-ocean ridges. Huge volcanic systems, right?
The most extensive on the planet. Plates pull apart, mantle rock rises, melts due to decompression, and erupts basalt along fissures parallel to the ridge.
Forming pillow lavas.
Yep, pillow lavas and hyaloclastites, that fragmented glassy stuff from rapid quenching in water. Plus, you get hydrothermal vents, black smokers associated with them.
Okay. Then convergent boundaries, where plates collide.
Yeah.
That's where we see volcanic arcs.
Exactly. Most of the volcanoes we see on land are in these settings. An oceanic plate subducts, releases fluids, triggers melting in the mantle wedge above it, magma rises.
Forming island arcs if it's ocean collision.
Right, like the Marianas or the Aleutians. Often starts basaltic, evolves towards andesitic stratovolcanoes over time.
And if ocean subducts under a continent.
You get continental volcanic arcs, like the Cascades or the Andes. Wider range of magmas here, andesite, rhyolite are common. Build big stratovolcanoes, can be effusive or explosive. The whole Pacific Ring of Fire is basically this.
What about continental rifts, where continents pull apart?
There, the lithosphere thins, asthenosphere rises, decompresses, melts, produces basalt.
Basaltic eruption.
Can be fissure eruptions, cinder cones, big flows, but sometimes that basalt ponds in the crust melts crustal rock or undergoes changes, leading to more evolved magmas like rhyolite.
So you can get explosive eruptions too.
You can. It's often a mix. Can even build stratovolcanoes sometimes, like Kilimanjaro in the East African Rift. You find large basalt flows and ignimbrites in rift zones.
And then hotspots, those isolated volcanoes, like Hawaii.
Thought to be plumes of hot mantle rising from deep within the earth, independent of plate boundaries.
So the plate moves over the plume.
Exactly. Creates a chain of volcanoes, like the Hawaiian Islands. Active volcano is over the plume, older ones trail off.
And they produce mostly basalt.
Typically voluminous basaltic magma, low viscosity.
Yeah.
Builds those huge shield volcanoes from successive thin flows. Can cause big submarine landslides too. These things are massive.
What about Iceland? That's a hot spot too, isn't it? When it's on a ridge.
Yeah, Iceland's special. Hot spot right on the mid-Atlantic ridge. Much more intense volcanism. Fissure eruptions, cinder cone chains, eruptions under glaciers causing those Jökulsá glacial outburst floods. Surtsey's formation was Icelandic hotspot volcanism.
In continental hotspots, like Yellowstone.
Similar idea, plume under a continent. But here, the hot basaltic magma from the plume interacts heavily with the thick continental crust.
Melting the crust.
Yeah, heat transfer melting generates silica-rich felsic magmas like rhyolite. So you get both basalt flows and highly explosive rhyolitic eruptions.
Leading to supervolcanoes.
That's the setting. Immense pyroclastic flows, ash clouds, giant caldera formation. Yellowstone's geysers and hot springs today are the lingering heat from that system.
Finally, flood basalts. They sound enormous.
Truly vast. Huge outpourings of very fluid basalt from fissures covering enormous areas, creates large igneous provinces or LIPs.
Like the Columbia River Plateau or the Siberian Traps.
Exactly. The idea is a massive mantle plume head hits the base of rifting lithosphere, causing widespread decompression, melting, and eruption along huge fissure systems.
Potentially impacting climate.
Oh, potentially huge impacts, linked possibly to mass extinctions.
So volcanoes are clearly creators, but also destroyers. Let's focus on the hazards now. What are the main dangers?
They pose significant risks, especially as more people live near them. We need to think about the erupted materials themselves and secondary effects, too.
Okay, lava flows first. Destructive, but maybe slow enough to escape.
Usually, yes, people can evacuate from basaltic flows, but they destroy everything in their path: homes, roads, farmland, Huge property damage. We've seen that clearly in Hawaii and at Etna recently.
And the pyroclastic debris, ashfall.
Ashfall can be a major problem over wide areas. Close in, the weight, especially when wet, collapses roofs. Further out, it disrupts travel, contaminates water, damages crops, gets into machinery. Pinatubo in '91 showed how far-reaching ash impacts can be.
But pyroclastic flows, those seem like the most immediate lethal threat from explosive eruptions.
They are terrifyingly deadly. Super fast, super hot avalanches of ash, rock, gas, 100s of kilometer, 500, 1,000 degrees Celsius.
Nothing survives that.
Virtually unsurvivable. Flattens and incinerates everything. The destruction of St. Pierre in Martinique in 1902 is the classic, tragic example.
And lahars, volcanic mudflows.
Lahars are dangerous too. Slurries of volcanic debris and water from rain, melted snow or ice, crater lakes.
They flow down to valleys.
Rapidly. Carry huge boulders, trees. Immense force because they're so dense. Bury everything. The Armero tragedy in Colombia in 1985, caused by a lahar from Nevado del Ruiz. Devastating loss of life. A terrible reminder of their power.
Beyond the erupted stuff, what other hazards come with volcanoes?
Several others. The blast itself, think Mount St. Helens' sideways blast in 1980, flattened forests.
Landslides, too.
Yes, magma movement or eruptions can destabilize slopes, triggering massive landslides. And the magma movement causes earthquakes, which can cause damage even before an eruption. Definitely a risk, especially for island volcanoes or coastal ones. Big explosions, caldera collapses, large submarine landslides can all displace water and generate tsunamis. Krakatau is a famous example.
And gases, even without an eruption.
Yes. Gases like CO2 are denser than air. They can seep out and accumulate in low areas, displacing oxygen. Deadly asphyxiation hazard. Lake Nyos in Cameroon in 1986 was a tragic case of this.
And we can't forget the impact on airplanes.
Absolutely critical hazard now. Fine ash is abrasive, damages engines, windows. Worse, it can melt in hot jet engines and then resolidify, causing engine failure.
We've seen flights grounded because of eruptions.
Many times. The Eyjafjallajökull eruption in Iceland in 2010 shut down European airspace for days. Huge disruption. Ash is a serious threat to aviation.
So with all these dangers, how do scientists work to protect people? How do you mitigate these risks?
Well, the first step is understanding the volcano itself. Is it active, dormant, or extinct?
That's the difference.
Active means it's erupted recently or shows signs of unrest, likely to erupt again. Dormant hasn't erupted in a long time, but could. Extinct is considered incapable of erupting again.
How do you tell?
Look at historical records, age date the rocks, understand the tectonic setting, check how much it's eroded. Kilauea in Hawaii is very active. Mount Rainier is dormant but potentially dangerous. Devil's Tower is an extinct volcanic neck.
And predicting when an eruption might happen? That seems incredibly hard.
It's a huge challenge. Long term, we can look at past eruption frequency, the recurrence interval, but it's just an average, not a precise timetable.
So short-term warnings are key. What signs do you look for?
We monitor closely for changes. More earthquakes as magma moves. Changes in heat flow, maybe melting snow or ice. Changes in the volcano's shape, bulging as magma pushes up.
How do you measure shape changes?
Using lasers, tilt meters, GPS, satellite radar like INSAR. Very precise measurements. Also, increases in gas and steam emissions or changes in their composition, new hot springs appearing, all potential clues.
So it's like listening for the volcano to wake up. Once you suspect something, what practical steps are taken?
Hazard assessment maps are vital. They show which areas are most at risk, from lava flows, lahars, pyroclastic flows, etc.
To guide planning and evacuations.
Exactly. The successful evacuation around Pinatubo before its '91 eruption, based on maps and monitoring, saved thousands of lives.
So monitoring teams are crucial.
Absolutely. Round-the-clock monitoring. But deciding when to evacuate is tough. There was controversy around the Guadalupe evacuation in 1976, for example. It's a difficult call.
Can you actually divert lava flows?
People have tried. Building barriers, like on Etna, using explosives, even cooling the flow front with massive amounts of water. They did that successfully in Jaime, Iceland in 1973 to save the harbor.
Amazing. Now, shifting scale again, can eruptions affect global climate?
Oh, most definitely. Ben Franklin noticed it back in 1783 after an eruption in Iceland caused a haze over Europe.
How does it work?
Big explosive eruptions inject fine ash, but more importantly, sulfur dioxide, SO2, gas way up into the stratosphere. Up there, the SO2 forms tiny sulfuric acid aerosol droplets, creates a haze layer that reflects sunlight back to space.
Cooling the planet.
Temporarily cooling the lower atmosphere, yes. The Tambora eruption in 1815 led to 1816, the year without a summer. Widespread cooling, crop failures.
How long does the cooling last?
Months to a few years, depending on how much SO2 gets up there. Evidence from ice cores they trap sulfuric acid layers and tree rings confirm these past climate impacts.
And maybe huge flood basalt eruptions caused longer-term climate change, linked to extinctions.
That's a major hypothesis, yeah. The Siberian Traps eruption coincides with the end Paleozoic mass extinction. The scale is immense.
What about the Toba supereruption? Did that affect humans?
Some scientists think Toba caused significant long-term cooling tens of thousands of years ago, maybe even leading to a human population bottleneck. It's debated, but possible.
And maybe influenced art and literature. Turner's Skies, Frankenstein.
Possibly. The gloomy atmosphere after Tambora might well have inspired artists and writers like Turner, Byron, Mary Shelley. A Krakatau-sized eruption today might cool the planet by maybe 0.3 to 1 degrees Celsius.
Incredible that a single event can have such global reach. What about the long-term role of volcanoes in civilization and Earth's history?
They've played a huge fundamental role. Early volcanism helped form our crust, atmosphere, oceans through outgassing.
And maybe help life originate. Hydrothermal vents.
That's a leading theory, yeah. Vents on the ocean floor linked to volcanism. Over time, volcanoes create fertile soils for agriculture, provide mineral resources. We see ancient human footprints in volcanic ash. We've lived with them for a long time.
But they've also destroyed civilizations, Santorini and the Minoans.
That's another strong possibility. The Santorini eruption could have severely impacted the Minoans through ashfall, earthquakes, tsunamis, and their power led to religious beliefs too, like Pele in Hawaii.
A complex relationship, for sure. Before we wrap up, Earth isn't the only place with volcanoes, right?
Not at all. We see volcanism across the solar system. The moon's dark maria are ancient flood basalts.
Venus, Mars.
Venus has lots of volcanic features. Mars has Olympus Mons, the largest volcano known a giant extinct shield volcano.
In active volcanism.
Jupiter's moon Io is incredibly active. Hundreds of volcanoes spewing sulfur and basaltic lava driven by tidal forces.
Well, icy moons.
Saturn's moon Enceladus has geysers erupting water vapor and ice cryovolcanism driven by internal heat. It's fascinating to see these processes elsewhere.
Truly amazing. So as we finish this deep dive, what's the big takeaway about volcanoes?
I think the core message is they're much more than just mountains that erupt. They are fundamental, powerful geological engines. They've shaped our planet profoundly: crust, atmosphere, oceans, climate, fertile land, resources.
And hazards, too.
And hazards, absolutely. They are a direct expression of Earth's internal heat and dynamism.
And understanding them from the magma details to the global impacts is just crucial, both for safety and for appreciating our planet.
Exactly. Essential for mitigating risks and understanding Earth's ongoing evolution.
Okay, so here's a final thought for you, our listeners. Given how interconnected Earth systems are, what other, maybe unexpected ways might volcanoes have influenced our planet's history and the story of life? Something to ponder.
Definitely keeps scientists curious.
And with that, we've reached the end of our deep dive. We've covered the full story presented in the source material, the types of volcanoes, what they erupt, how they erupt, the hazards, prediction, mitigation, the different geological settings for mid-ocean ridges to hotspots, their climate effects, and even volcanoes on other worlds.